Hi everybody, welcome back. Today we're going to continue talking about the chemical structures like we did yesterday. This time we're going to focus on line structures, which is kind of the final step in being able to express organic structures properly. Before we get into that, I just want to do a quick review. So this is from the materials that are posted in Teams under Module 2. There's lots and lots of practice problems in there, so you'll be able to both practice and then also test yourself to see how well you're doing with this stuff. The reason that we want to do this first is because you definitely want to have some facility with this before going to the new line structure. So we're going to start with, again, our condensed structures from yesterday, and then we'll move into the line structures. All right, so let's try one of these. Let's look at I, this one right over here, and we'll see what that one looks like. So we got CH2, 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 O, CH3. There's nothing strange here. There's no parentheses or other things we have to worry about. It's just a standard linear structure. So what I always like to do if we're trying to draw a Lewis structure there is just expand it out, but keeping the groupings together to give us a sense of how it's connecting. So that means for this one we might go CH3, CH2, CH2, O, CH3. So we have something like that. And now it becomes a lot easier to make the full Lewis structure by expanding out those hydrogens on each of those atoms. So we can go like this to get our basic structure, and then add in those hydrogen atoms as well. And that's a good Lewis structure for that molecule. All right, let's look at one that's a little bit trickier with these, maybe something with parentheses, double bonds, things like that. Let's look over here at F. So for this one now, we've got, let's see here. We've got a couple different things going on, right? We've got these parentheses around CH3, CH2, so that whole thing is going to be taken twice. And then we also have this double bond coming out that way, so that gives us a little bit more of a challenge. Now remember, there's a couple different ways to interpret parentheses. Sometimes the parentheses means just those many things connected in a row. Other times it doesn't, and the way we know whether it is or it isn't is we go back to those original rules and think about what would happen if we connect these things in a line? What would there be enough bonds on everything or not? Another good clue about that is if you see CH3, then you know that's not something that can go in a line because CH3 already has 3 connections on it, right? The CH3 is this. And so there's only one spot that it can be connected. So it can't have anything on the other side because that's it. So when we see CH3, we know that has to be a terminal, an end of something. So that means that these two CH3, CH2 groups, right, the two things in the parentheses here, actually have to be separate groups, not connected to each other. So CH3, CH2, and then CH3, CH2. Those are those two groups right there. All right, so then next we have just a C. So we'll think about how that's connected in a minute, and then that's going to have a double bond to the CH2. So hopefully you can start to see here how these things have to be connected. This carbon needs 4 total bonds. It's got 2. So these 2 pieces must each connect to that carbon. Oops. And the reason that we know that they have to connect to the carbon and not to each other is because if the CH2 tried to wrap around and connect to this other CH3, there would be too many bonds on the carbon. So that's our almost Lewis structure, and then you can expand that out by drawing the rest of the hydrogens. So make sure you're kind of comfortable with doing this. Try the rest of them. Show them to me if you have questions or if you're not sure if you did something right. Hopefully that's going okay for you. All right, let's move it on to the next step. So you'll notice I have some, we'll come back to these as well, but I have another page here called line structures. And these are, again, I've just copied in some of the practice problems from the sheets that I posted on Teams. So that's all these are. We'll come back to them, but I just wanted to show you first. This is what I'm talking about when we say line structures. This is what they look like. These are kind of like the structures you saw of those dye molecules. And we'll be using those to look at the structure of our biodiesel molecules a little bit later today, if there's time. Otherwise, we'll do that next week. So here you can see very different looking things. Right? You see these kind of shapes, these zigzag lines, not the same as the condensed structures or the Lewis structures that we looked at just before and yesterday. So where do these things come from? We should also note that these are sometimes called skeletal structures. I don't remember which words the reference that I gave you uses. Also maybe bond line is another one I've seen. But they all refer to the same thing. I usually just call them line structures. Okay, so where do these things come from? Well, to figure that out, let's look at some molecules that we know and look at the condensed structure, the Lewis structures, or the condensed structures and the line structures, and see if we can start to see some comparisons. Or some similarities. All right, so let's start with one of the molecules we looked at yesterday, C3H8. A condensed structure of C3H8 might look like this. And I'm going to draw the lines in between so that you see the connections. So CH3, CH2, CH3. The line structure for that would look like this. And I'll explain it in a minute. Let's just look at some examples first. Here's another molecule we didn't look at yesterday. Okay, similar, one more carbon. That one looks like this. So hopefully you can start to see what's going on here. Let's label our atoms and see what's happening. In this, we can say this is carbon 1, 2, and 3, if we label our carbons. And the corresponding carbons over on the line structure then are 1, 2, and 3. If this one we call 1, 2, 3, 4. 1, 2, 3, and 4. So hopefully you're starting to get at least a sense of what's happening here. We're basically getting rid of the carbon atoms and the hydrogen atoms and instead making lines where the ends of the lines and the places where the lines intersect represent carbon atoms. So the two basic rules of line structures are, first, carbon atoms are assumed to be at the ends and intersections of lines. Communication with the tablet's been a little slow again for some reason. All right, so wherever we have an end of a line or lines intersect, we assume there's a carbon atom there. Okay, well, what about the hydrogen atoms? Well, that's going to be our second rule. We're going to assume there's always enough hydrogens so that each carbon has 4 bonds. All right, so we're using our rules from yesterday to allow us to simplify the structure, just like we did with the condensed structures. If we know that carbon has to have 4 bonds, then let's take a look at these, like this line structure right here. So at number 2, carbon number 2 here how many bonds are shown to different carbon atoms? 1, 2, 3. See that? 1, 2, and 3. So that means there must be one more bond here that's not shown that's a hydrogen atom. So we can always figure out how many hydrogen atoms are on a given spot just by that rule from last time. Right? Just knowing that carbon has to have 4 bonds, so we know the rest of the stuff has to have carbons. If we look at number 1 or number 3 here, or 4, there's one line shown. There's one connection shown from this carbon to this carbon, from 1 to 2. And so there must be 3 other connections there somewhere because carbon has to have 4 bonds. And those 3 must then be hydrogens. They have to be hydrogens so that we can fill that up, so that must be a CH3. All right, so one way to practice this is to look at existing line structures and try to figure out how many atoms are on each spot. So that's kind of what this first set is for. So let's take a look at this structure over on the left. So if we want to know, let's say, what's the molecular formula? How many carbons, hydrogens, whatever are in here? We can start by first just drawing in the carbons at each spot where there's going to be a carbon atom and then adding the hydrogens. So that's going to be here, 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 here. So every spot that 2 lines come together, or every spot there's an end of a line, we're going to put a carbon atom there. And then, to figure out how many hydrogens are on each one, we just subtract from 4 based on how many bonds are already shown. So these carbons at the top here have 1 line coming off of them, so they must have 3 more hydrogens. So we can add our 3 hydrogens, so that's going to be CH3, CH3. I put the H3 before the C just for symmetry, and so it didn't run into the other stuff, but it doesn't matter how you do that. If we go to this next one then in the middle, how many bonds are shown to this one? 1, 2, 3, 4 bonds. So that must mean that there are no more hydrogens on that carbon. That one just stays as is. Moving on to the next one. 1, 2, 3, 4 bonds shown. So there's no more room for hydrogen. And then the rest of these 4 are all the same because they have 2 bonds shown. So that means there must be 2 more hydrogens there to make a total of 4. So each of these has to be a CH2. All right? So now we essentially have a condensed structure for this molecule. And if we want to know the molecular formula, we just add everything up. 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. So the molecular formula for this compound should be C8H14. And in that way, we kind of decoded the line structure. All right, so what happens, let's take a look at some of these other ones. What happens when you have other atoms that aren't carbon and hydrogen? For example, let's see, where's one with an OH? This one, E here. So one thing that I want you to do first is ignore these dots. Those are called lone pairs or non-bonding electrons, and they're important for organic chemistry for trying to figure out how these reactions work, but for our purposes, we're not really going to use them. So you can ignore those dots for now. What I do want you to think, though, is notice how these non-carbon atoms are written. Notice that nothing really changes. O is still O, and if there's a hydrogen attached, the hydrogen is still shown. So you can't just write O and assume there's another hydrogen there, and that's because something I didn't really tell you yesterday, those rules are not quite as they're not quite as true all the time for atoms that aren't carbon. So we can say carbon's always going to have 4 bonds. We can't really say that about oxygen and nitrogen and other things. So the other atoms all stay the same. So let's go back and write a third rule here. So other atoms that are not carbon, non-carbon atoms, are not changed, and their attached hydrogens are always shown. All right, so we're not going to mess with those other atoms. That also means if we go back to our rule 1, carbon atoms at the ends of lines, if there's another atom there, like right here, there's not a carbon atom right there. Oh, hold on, I'm getting a lag again. Give me a second to let that catch up, I think. Here it comes. So I already drew this, but there's a, there it is. Okay, caught up. So at that spot there, there's no carbon atom there, even though that is the end of a line. That is the oxygen. That's where the oxygen is connected, not the carbon. Same thing up here with that other oxygen. Anytime there's some other atom that's not carbon, there's no carbon at that spot. So knowing that now, we know all the rules, we know how these line structures kind of work. Let's try to draw some. So let's take a Lewis structure like this one here, and let's draw a line structure for it and figure out kind of a technique to do that, or a strategy for doing that. All right. So one thing that we have to do when we draw successive carbon atoms, as you saw in some of the examples, is we have to zigzag it. And there's two reasons for that. One is that that's how the shapes of molecules actually are. They're not straight 90 degrees. They have these angles that are not 90 degrees. The other reason is you wouldn't be able to tell how many different carbons there were, because it would just look like a big straight line. When I see a bunch of carbon atoms together like this in a row, and I want to draw a line structure, what I usually do is I just number or count them. And you don't have to do all of them, but the ones that are all kind of connected together. And that's going to be my main zigzag. So then I go, okay, there's 5 in a row. So I can draw a zigzag of 5 carbons. And it doesn't matter which way I start, up or down, but I want to make sure that I've drawn 5 carbons in a zigzag line. So that's going to be 1, 2, 3, 4, 5. And then it's always a good idea to transfer those numbers just so you make sure you did the right amount. All right, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We've got those 5 carbons. Now that we've got something to work with, we can start branching off the other stuff. So for example, I can see that at carbon number 2, there's another carbon coming off of it. So coming off of carbon 2, I can draw this other carbon. And then coming off of carbon 4, there's 2 more. There's one up, one down. Now we don't have to do the same directions, but we have a couple choices here. The most obvious way is to go like that, and that's okay. That's okay to do. But when you look at the example structures, you'll see generally we try to maximize the angles because the atoms are going to want to kind of repel each other. They're going to want to spread out as much as possible. So rather than draw them up and down, you'll usually see these drawn kind of like this, so that they're spread out a little bit more. But that's our line structure. So if we called those 1, 2, 3, 4, 5, maybe we'll call these ones that are coming off A. We don't want A, B, and C. That's like the carbons. Let's call them X, Y, and Z. So then I've got my X, Y, and Z. The reason I'm able to draw them at different angles like that is that single bonds between atoms can rotate freely. So however you want to spin things around and draw them is okay. All right. I'll leave these other ones for you to try, but I do want you to try them, so please do that. And then let's look at one of these other examples here where we have to go from a very condensed structure all the way out into a line structure. Let's see what we can do here. So let's take a look at O right there first. So because the line structure kind of gives you more information about how things are connected and what the overall molecule looks like, it's actually better than the condensed structure in that respect. So I like to take the very condensed structures like this and first expand them out so that we can really see how many atoms we're dealing with and how things are connected. So CH3 taken twice, we know those can't be in a row, so they must be both connected to that C. Then I've got the double bond to the CH, and then the CH2 and CH3. So that's my like expanded structure. And then from that, I can start putting together this shell of what's going to become my line structure. So how many carbons do I have continuous in a line? That's like 1, 2, 3, 4, 5, right? Now, could I have just done 1, 2, 3, 4, starting with what we've got number 2, and then add the other ones on from there? Sure, that's fine. But I've got 1, 2, 3, 4, 5. So that means I can do a 5-carbon zigzag. 1, 2, 3, 4, 5. If you went the other way and made it more like a W, that's fine. And then I can make sure my numbers transfer. That all looks good. So now I just have to add all the other structural information in here. So for example, between carbon 2 and 3, there's a double bond. That needs to be expressed in the line structure as well. And so all we have to do is draw a second line between 2 and 3 right there. That shows our double bond. And then the other thing that's not shown here is there's an additional CH3 coming off of carbon number 2. So we need to add that, and we're going to add it up because that is expands the angles the most, has the largest angles. If we went down, it would kind of like look squeezed in between those other ones. Whoops, lost my double bond. So I'm going to make it up. And you'll notice that carbon 1 and this other carbon are actually symmetrically equivalent. So, you know, we could think of this as carbon 1 up here, and this one is that extra carbon as well. That would be fine too. But there you go. There's a structure for that one. All right, let's do one more example where we have some other stuff to deal with as well. Let's look at F. So same thing, I first want to put together my condensed structure, or expand the condensed structure out a little bit, and then I'll add in, then I'll make the line structure and work with that. So for my condensed structure, I've got, again, 3 of these pieces in parentheses. So we'll start with those, and we'll draw them out as 3 pieces, CH3, CH2. We know they can't really connect to each other because then there would be a CH3 with an extra bond, which would have 5 bonds on that carbon, which we can't have. So these must all just connect one time to something else. And then we've got this C and OH. So looking at that, we can see that those 3 big pieces all have to connect to the carbon here. And so knowing that, I can kind of, let's say, redraw this a little bit to make that a little more clear. So maybe I'll go like CH3, CH2, you know, just to kind of show that this is all connecting. In terms of how you draw it or how you draw the angles, it doesn't really matter because we're just trying to get a sense of what this thing actually looks like so that we can ultimately draw our line structure. Now there's a couple ways to draw this line structure, and I want to show you a couple different possibilities for that. So one would be to just kind of focus on the middle line like we've been doing and call this 1, 2, 3. So that would give us a 3-carbon zigzag, 1, 2, 3. And now I can start adding other stuff that's connected. So over on the right, I've got the OH. Remember, we're not going to mess with that. We're not going to cut off the H. We're just going to add that. Additionally, watch that I put an extra line in here. Whoops. So I can't just put the OH here because now I don't have a carbon here anymore. I have to have another line with the OH so that I still have carbon number 3 and then the OH connected from there. And then I've got these other 2 carbon pieces coming off of number 3. So I can kind of go like this and like that or something like that, and that works out okay. The other way to think about this, maybe I'll use a different color, is to notice that some of these carbons are connected in a little bit bigger chain. So what if we kind of went around like this and thought of this as a 1, 2, 3, 4, 5? Even though it's sideways and it's like a different orientation, things are still connected in the same way. So for that one, we might do a 5-carbon zigzag. And we have to be a little bit more careful about what we put where. We still have the OH coming off of number 3. And then we also have this extra piece here coming off of number 3. So something like that maybe. Those two structures, the green one and the blue one here, look different, but they're actually the same. They're the same molecule. And one thing that can be helpful to figure that out, if you want to try while you're on campus, when you have some extra time during lab, is to use a model kit where you can actually put the pieces together and show that they're the same. So for the last thing today, we're not going to have time to get into the biodiesel molecules. We'll save that till next week because I don't want this to go too long. But I do want to just make a quick model of the structure we just drew so that you can see that those are indeed the same. So I've got some little pieces here. And I'm not going to put all the hydrogens on. We're just going to look at the carbons and the oxygen. So I'll use my green one to start with. So I'm going to make a model of the green one. I'll try to do it up here so hopefully you can see in the camera, but I have to move around to get the pieces. If you're watching this later, you can kind of fast forward until I've finished building the thing. All right, so there's my 5 in a row. So now coming off of this middle one, I'm going to have the OH. So I'll use red for that. O. And I'll put the H on there too, just like with the line structures, we don't abbreviate that. So here's my O and then H. Okay, like that. And then the other additional spot there is going to have my other 2 carbons. So 2 more carbons coming off of there. So look at the shape a little bit there. This is one thing we didn't really talk about, but one of the consequences of carbon making those 4 bonds is when it has 4 things connected to it, like this middle one, it doesn't go in a flat T shape, because that would actually, a T shape would have 90-degree angles. And as you can see, these angles are wider than 90 degrees. They're about 110. So by expanding into 3 dimensions, those atoms can be further apart from each other and therefore not repelling each other as much and more stable. So that's another reason it's nice to see those model kits this way. So if that's my, let's see. So if that's my green structure, we should be able to actually make the blue structure without disconnecting anything if they're the same. So I'll put my OH over to the left here, and then I have my 1, 2, and 3 like this. And I mean, it's not going to look exactly the same, but you can see how these other 2 pieces are kind of reaching down, just like in our drawn structure. So you can see how, hopefully you can see how that is actually the same. I didn't disconnect anything, I just twisted things around, and I was able to do that. All right. So when you are checking your structures to see if your structures are correct or not, the key thing you want to pay attention to is the connectivity. Is everything connected to each other the same way it was in the structure you were trying to replicate? So is number 1 connected to number 2, connected to number 3? Is the OH coming off of number 3 and not number 2, and so on? So that's what you're looking for when you are drawing these structures. All right, so for your work this week, please work through this. If what I'm saying isn't helpful enough and you want a little more information, there is a great document on Teams that talks about this in more detail and shows more examples. You can read through that for some more help. Work through all of these structures as practice so that you know that you can draw these things. And then go back, there's a few other examples too, such as like finding formulas. If you can do all of that stuff, you should be good for this particular objective. And then at midterm, this is definitely one of the ones we're going to check. So, you know, can you draw a proper line structure of a particular formula? Can you interconvert between condensed and line structures and Lewis structures? So please work on that and let me know if you're having any trouble or you need any additional help. And I will see you all soon. Bye.